Okay, so today I am going to show you a bit of forbidden research. We're going to look at a paper that I have received anonymously and that is published anonymously. It's called ABRMsNet and Attention-Based Residual Multiscale CNN for Image Classification. Can't really tell you much more about the paper itself. It's a very interesting read. It's amazing. I can't leave you a link to the description of the paper because it's I can't tell you how I got it. But so overview of the paper of this particular research paper, the attention-based residual multiscale convolutional neural network, or ABRMsNet, is a deep learning model designed for image classification, particularly for complex medical images such as brain tumors. The model is built upon CNNs but integrates 4 different attention mechanisms to capture multi-scale features and improve classification performance. So kind of like overview of this overall. So a big thing, like the reason why I'm making this video overall is for this particular reason. Like a lot of people think that the best way forward at the moment will be just like throwing things at LM models or transformer models, right? Because they can do these things. So when it comes to specifically like medical images and scanning them and looking at them for brain tumors, things like that, like BERT models, other models, like transformer models have and are, and I can show you in this notebook, trained on these types of concepts as well, and they can do them. The problem is accuracy, speed, performance overall, etc. Right? Like it's just flat out not the best model overall for these things. And not having the best model overall for these things is okay when it comes to some things, but when it comes to detecting brain tumors, do you want like a okay model, or do you want the very best model that's out there? I want the very best model that's out there, right? Just like flat out. And then so when it comes to those types of things and those edge cases and increasing performance, you still have a lot of play within these different types of architectures, right? And CNN is like the most classic architecture that you can get. Like as far as modern AI, like CNN models are like the grandfather of modern AI. And the fact that we can still make gains on CNN models in 2025 shows you that there's still a lot of play within this, right? And then so essentially, we're just like this model and this research is essentially just taking CNNs and bringing them into 2025. We're like multi-head attention. In this instance, it's 4 attention layers and 4 individual attention layers, which essentially the components are of the components of the attention, right? Are there's a self-attention block, a global attention block, a channel attention block, and a spatial attention block. And then self-attention is directly inspired by transformers, so it's taken directly from that. Global attention uses multiple pooling methods, so average, max, minimum, global average, to extract all of the dominant features. Channel attention block weights the importance of different features channels dynamically, and spatial attention block highlights important spatial regions in an image. So you put all of these things together, all of these different attention mechanisms together, and what I'm referring to with in regards towards brain scanning technology, it's able to get 99.47% accuracy. So with these models, like 100% accuracy overall is hard to achieve, right? Like it's like, and especially like on a tumor type of data set, like straight like 100 is very hard. And then I'll show you and actually lower down in this notebook where I'm getting 100, and I'm not fully measuring it out, and it's also a more simple data set, but highlighting that overall. And so diving into this, into the model itself, right? So what I can show you, and I'll link this Colab notebook to you so you can have full access to this Colab notebook. Let's first start off with like taking a look at this model, right? So I build out an example of this model. So we have essentially our multi-scale convolutional block. So we're creating a CNN model, and then I define the attention mechanisms, all 4 of them. It's super cool, right? So spatial attention, and then you like all 4 essentially come and are combined together into your overall neural network here, and then we just train the model And I start training it essentially on the data set here just to make sure that I'm accurately representing this. And you'll notice this a lot through this notebook. I'm stopping the training within this, right? If you pay attention to a lot of my videos and what I put out, I do a lot of research. I'm researching a lot of different things, and then so within that, the most important thing within my research is compute, right? Compute plus time are the two things. And then so when it comes to like training a CNN model, I'm flat out training these CNN models from scratch, right? So I'm building them from scratch and I'm training them. And like typically that's a long process for each model, like 4+ hours for each model to fully train it out from scratch. I'm not trying to go through like a full training process on each one of these models, right? I want to let's get enough so that I can extrapolate the results further from that, and then so from there it's to me 2 epochs. So we go from our initial accuracy on our first epoch is 56% accuracy with a value accuracy of 82%, which is something that's gonna go up, right? And then on the second epoch I get accuracy of 83%, and I'm assuming that value accuracy is going even higher in order to clock us at that 83%, which means that very realistically, by the end of this test, we're going to get very close to, if not above 99.97%. And this is on Fashion MNIST, so I expect that kind of straight out there, right? And then so the next test that I do within this and highlighting it as well is like I try to like essentially build out the full architecture of this and put it into a transformer model, because that's like what like people want, like I'm assuming would want to do as the next step within this, right? Like so all of what I just said at the top, that like these CNN models are different than transformer models overall, and they give you advantages. Next question people ask is like, well, can you put it in a transformer model? Sure, you can do all of this is just math, right? So I can combine math. And then so in this instance, I can combine this CNN model with transformers. And then what we have here is a transformer layer that is a multi-head CNN transformer layer that has all of these attention layers within it. But the thing is so when it comes to transformer models as opposed to CNN models, transformer models generally inherently have more attention heads, generally speaking, the modern ones, than 4. Like your BERT models even will typically have like 12 or 8 attention heads as opposed to 4, right? So we'd actually be like we're reducing the number of attention heads within this transformer model overall, but you can do it. And then so highlighting that here's like your multi-head transformer model, right? And then so here's the model, just actually like what it would look like by itself, right? So not attention. We're just building out essentially your typical CNN model, which is just this is in this instance a 4-layer CNN model. And then just essentially printing out the structure of the model here. Very straightforward. I'm giving you just like, since I'm not linking the research paper to you, I'm trying to give you like, as much as you would want to take a look at these things and understand these things if you want to dive deep into them. And then so the next thing that I do here is I want to train this model and test this model versus BERT, right? So up until this point, I've talked about like utilizing and testing CNN models versus transformer models. And then so that's what I start to do here. And then so I run this test. And then again, this is another point where I stop the test, right? So in here, I run the test, like, so training my CNN model on like for 5 epochs on this particular data set, it was a breeze. It's super fast, super cool, right? I trained this BERT model it ends up being for 2 epochs, and then it took me like half an hour for these 2 epochs. And I was like, yeah, we're not going further than that. And then so I kill it there. But like, training the CNN model for all 5 epochs took a minute or less. Training the BERT model for 2 epochs took 30 minutes. So like that gives you a clear indication, right? Like why would you want to utilize these models like in the over just throwing it at a transformers, like performance, right? Like flat out, like yes, okay, you can throw every single problem that you would want to under the sun at a BERT model if that's what you truly want to do. But if you don't want to wait around for 4 hours to find out your answer to your simple question, then like knowing that CNN models and that you can do this and do it in a minute as opposed to 4 hours saves you a lot of time overall, and especially when you compound and you compute that out overall. And then so kind of like the next and getting into the last test that I want to do is like, can I actually turn this like into a full on neural network, and then also can I train it like like a neural network, right? And then so that's what I start doing in this instance, and start getting into. So I change the data set and I give it like I give it a tokenizer. So I give it the BERT tokenizer, and then I essentially like and I'm doing classification tests, right, again. And then so I train it as you would like a BERT transformer model, and then I'm getting 100% accuracy, and I only need to train it for like 2 epochs, and then it's just instantaneous, super fast, right? And then I did this multiple times, and then like it's this is a train test split. It's not training on the train data. Like it gets up to 100% accuracy very quickly with this model within this. And I'm assuming it's coming out like 99.9, right? But it's like it's measuring out 100. Like here it is. Across the board. And then so the next and the last thing I want to do is let me take this like to the full extreme, right? And then that's kind of what I'm doing, and I'm training out here. And then you can see it's been training for 1 epoch so far. And then so this data set that I'm training it on is a data set that BERT typically struggles with, which is why I wanted to utilize this particular data set and train it on this. But then again, like it's a large data set, and I'm training a model from scratch. So you can see it's going to take time to fully train out this model. Again, like 4 to 6 hours to fully train it out. And then so I'm not going to wait the 4 to 6 hours to fully train out what we're looking at here. But I do, so this model, I MIT license it. This is the 4-head CNN for NLP, an architecture inspired by the multi-head attention mechanism. So this 4-head CNN is a novel deep learning architecture designed to replicate the benefits of multi-head self-attention within a convolutional neural network, or a CNN. This model incorporates 4 parallel convolutional network layers, each acting as an independent attention head, extracting diverse contextual features from text sequences. By leveraging multi-scale feature extraction, the 4-head CNN attempts to match the performance of transformer-based architectures like BERT while maintaining the computational efficiency of CNN. So I can get better than the BERT accuracy and for far less compute. It's the reason why you would want to utilize this for text classification over a BERT model. So architectural overview. Input layer is just word and embedding tokenization. Model takes tokenized text responses as input. It's utilizing the BERT tokenizer in this instance. So it converts each token into dense vector representations automatically. And then the main thing is the multi-head convolutional feature, right? Extractor. So the core of the model consists of 4 parallel convolutional heads, each with a different kernel size. Each convolution head extracts different n-gram patterns, simulating multiple perspectives on the text. So kernel sizes are selected to capture word to phrase level dependencies from 3 to 6 kernel grams. It also incorporates global max pooling. So it's for compression and feature selection. Each convolution head outputs feature maps, which are compressed via global max pooling. And this selects the most important feature per filter, improving generalization of the model overall. Like these models and this particular 4-head CNN model, the forbidden research, is scoring very well on generalization overall, right? And that's like what I want to highlight and leave you with this model is, so the forbidden research is directly for like medical processing and medical research, and on like medical accuracy. But then on this test, so throughout like this particular video, I've shown you from medical research to fashion MNIST, which is like taking like literally like pictures of like clothing and fashion objects and then classifying that, down to classifying text like a straight up like hammer spam type text classification. And the model that we're looking at, this 4 CNN head extractor, is able to do it with modifications to the architecture across all of these things, right? Which means it's a generalizable model and generalizable architecture. It's kind of the beauty of this architecture. Very computationally efficient compared to transformers for all of the reasons that CNN is more computationally efficient than a normal transformer model. And it also gives you more robustness. This 4 attention head evolution is pretty cool. There's a lot of attention paid to the how exactly each individual attention head works, the layers work, and how they interact with each other. So really cool overall. The Forbidden Research isn't a publicly available research paper at the moment. So as soon as it is, and I see it publicly available, I'll link to it. But I'll leave a link to this Colab notebook. If you like this sort of content, please like and subscribe. Thank you very much.